So what's the overall rate expression for question 6? Our rate overall equals K2, yes, times concentration of chlorine to what power? How do you know it's first? Coefficient in step 2 is 1 times concentration of CHCl3. Okay. So we could go through and say, okay, that's our overall expression. However, do we know all of those terms, or can we calculate them? Okay, a rate constant, if we know our reactants, we can go ahead and figure that out. Okay. Do we know the concentration of chlorine? Just Cl, not Cl2. How would we figure that out if we knew the concentration? What would we need? We need to find out if it's a reactant in our overall reaction. How do we figure out what the overall reaction is? Add the individual steps of your mechanism. So when we add up those individual steps, what do we end up noticing? Does chlorine show up in our overall reaction? No. So what's the problem with using this overall rate expression? Don't know the concentration of chlorine. Well, if we don't know the concentration, how could we ever use this equation? We can't. Which ultimately means we have to do something else. So when we get a slow step that kind of happens in the middle, and we end up using the concentration of what's known as an intermediate, we have to do some other assumptions. Those other assumptions is that earlier steps in the reaction reach what? Equilibrium. What happens at equilibrium? The rate of the forward equals the rate of the reverse, and we can start to set things equal to each other. Pretty sure I'm going to run out of space here. Do you guys have that written down? I'll try and zoom in so I can see this a little bit better, or have the space to do this. Okay. Let's just cheat. More than one way to get white space, right? Okay, so what are we going to end up doing? What we're going to do is say the rate of our earlier step, so the rate for step 1 is going to equal the rate of the reverse. How do we end up symbolizing the rate of the reverse? Okay, the method that I chose, and I believe your textbook chooses as well, but I could be wrong on that, is -1. Okay, negative meaning the opposite of whatever the first one was. Okay, so we're running the opposite direction. What is the rate for the first step equal to? Don't tell me the rate of the reverse, but that's a good answer. It's equal to the rate constant for step 1 times concentration of Cl2. What's the rate of the reverse equal? Okay, -1 times be a little bit careful here. If we're looking at the reverse rate, where's our reactant? Left or right-hand side? It's on the right-hand side. When we're looking at our overall, or when we're looking at our rate expressions, we always put our reactant in here. So we're looking at Cl. What's the coefficient? 2. Because it's a mechanistic step, we know the order is squared. Okay, why does this help us? Well, when we looked at our overall rate expression that we determined from step 2, we didn't know the concentration of Cl. Okay? We now have an expression that tells us some information about the concentration of Cl. What we can go through and do is solve for the concentration. And what you should find that you get would be K1 over K minus 1. Cl2, right? I want the concentration of Cl. I'm going to run out of space here. K1 over K minus 1. How did I get rid of, or how do I get rid of that square? Square root the whole thing. Okay, why is this helpful? I now have an expression that gives me the concentration of Cl with respect to Cl2. Do I know the concentration of Cl2? If we look at our overall reaction, that is indeed something we started with. Well, presumably, if you start with it, you're adding it to the reaction. You also presumably know how much you're adding. So we do know the concentration of Cl2. What we can now do is substitute this back into our overall rate expression. Let's see if I can do that from memory. It's a bit questionable, but we'll see. Our rate overall, actually just work with the problem, was K2 times the concentration of Cl. We just defined the concentration of Cl down below. So K2 times the concentration of K1, K minus 1 with our square root, times the concentration of Cl2. We could throw in that square root again, except there's another format that we might want to use, because typically when we go through and come up with our overall rate expressions, we want to know what the exponent is, or the superscript, because that told us what information? The order for the reaction. How do we convert a square root into an exponent? Close. Oh, yeah. No, not quite. To the 1/2 power. I see where you're going with the negative, but not quite. Okay. We've now substituted in for our chlorine. So what we can go through and do now is add in our last little piece, CHCl3, to what power? First power. How do we know it's to the first power? Because it's the coefficient from that balanced equation. Okay. We now have the overall rate expression. You notice that looks pretty darn ugly. That's fine. It doesn't have to look pretty. Okay. And we now have an overall rate expression that we could use to determine other factors if we so chose. Okay. Since we've got this question up here, it asks what's the overall order for the reaction. Where do we find the overall orders? Sum of the coefficients, 1/2 plus an implied 1 gives us 3/2. Mathematically, this is what it works out to. Physically, do we quite know how to interpret or deal with that 1/2? I don't. Okay? So it's not something we necessarily need to worry about. At this point, this is what the mathematics is telling us of our solve. That's what's going to occur. Okay? What could have been the very first answer that in theory showed up on there? We said our overall rate was dependent on which step? So if we wrote out our initial overall rate, we might say it was the rate of K2 times what? Cl to the first order times 3, wouldn't it? Yeah. If this was the equation that you decided was the overall rate and was valid, what would your order come out to? 2. You'll notice that answer shows up there. Okay, why? It's the wrong answer. Okay, you need to know what you're trying to evaluate as you go through and process these. To determine the overall order for the reaction, you must have a usable and workable overall rate expression. The equation shown in orange is not usable because we don't know the concentration of Cl. Okay, kind of makes sense with the mechanisms. There is a lecture that goes over this a lot slower. Okay, so hopefully that will help out if you have some questions with this. Okay. So there's kind of the pseudo-cheating method for solving for A. A is going to be equal to your rate constant divided by e to the negative. Okay, so if you know the rate constant, the temperature for that rate constant, because remember the temperature changes with the rate constant, so you have to know the exact temperature at which the rate constant exists or has that number. The activation energy and R. Okay, R is the gas constant, you can look that up. So the question would give you your rate constant, your temperature, and the activation energy. I'm going to guess it didn't give you all of those. Yeah. Okay, so caught it. Okay, so there's another way to go through and approach that. Okay, and that is saying this equation is confusing as all heck. Let's try and reorient it so that it makes a little bit more sense. Okay, little bit more sense, not a whole lot more sense, but a little bit. Okay, I guess I do have a little space here. And what we're going to end up doing is saying, what's the most confusing part of the mathematics of this equation? E, probably the exponential factor there. So what we're going to do is try and get rid of that exponential factor. How do we get rid of it's not exponential, but we'll take the natural log of both sides and then try and rearrange. Let's see if I can pull this off in this space. So we'll get the natural log of k equals natural log of A minus, okay. I did skip a mathematical equivalency there. The natural log of a constant times some other number or sequence of numbers is the same as the natural log of the constant plus the natural log of the other value. The natural log of e to the negative EA over RT, natural log and e cancel. So what we end up doing is adding the negative, because we have the negative sign there, and we end up with this expression. Yes, no? Does that mean I should work that out? Seeing some quizzical faces. How about if you need problems with that solve, you talk to me after class? Okay. The next thing that we can do is try and rearrange this a little bit. Okay. Experimental values. What things can we get from an experiment? The activation energy is an intrinsic property of an individual species or an individual reaction. Okay? So we can't really do an experiment to measure the activation energy. What we can do is a sequence of experiments that would then allow us to determine it later on. Okay? So what would we measure in an experiment? Temperature is a very good thing to measure. Okay? So we could measure our temperature. In this case, we'll do 1 over T. I don't want to do it quite there yet. Let me shift it over. Okay, I can't completely remove 1 over T away from the activation energy over R. So what we're going to do is slide that in front here and get negative plus the natural log of A. So we said 1 over T was nice because we could measure or determine the temperature. A is something we were trying to figure out to begin with, so that's a little bit tricky. Activation energy, we said, is intrinsic to an individual reaction, so we can't really get that one easily. R is nice, but that stays constant. The only thing left is K. What was K? The rate constant. Can we calculate a rate constant? Yes. Just like we've done before with all of that data, we can go through and solve for a rate constant. So the other thing that we could determine or measure would be our rate constant. So why am I highlighting it in this fashion? Does this format look kind of familiar? To solve for the activation energy, what we can do is plot the natural log of K versus 1 over T. The slope of that line should be negative EA over R. So we could determine the activation energy, because we should see a straight line. What would the y-intercept be? Natural log of A. Okay, so B equaled our y-intercept, which equals, let's pretend that says intercept, which equals natural log of A. If B is some constant, how can I solve for A? How do I get A by itself? Need to get rid of that natural log. How can I get rid of the natural log? Raise everything to the e power. What I get is A equals EB, or e to the b power. I now have the value for A. To do that, we have to plot stuff. Not particularly fun. Most experiments don't force you to do that. Okay, so that's one way to do it. I think the other way depends on the experiment. You can go through and use a slightly different manipulation. It's the equation I don't remember. I think it's where you set activation energies equal to each other for two experiments. So there's three equations that come out of the Arrhenius expression. We've looked at one, that's our k equals blah, blah, blah. The other one is our y equals mx plus b format. The last one is ultimately just a solve of one of those, where you set two conditions equal to each other. Kind of boring. Okay, does that work?
Yeah, okay, so one of the questions is you had to do another table of L and K in 1/t.
Yes.
If you did all that, how do you go about plotting that?
So there's two ways you can do it. One, you do it by hand. The other way, come on, close. You would open up some graphing program. I use Excel, so if I was ever going to do this, you'll see me show it in Excel. You would say we've got 1/t, natural log of k. Oh, these are usually pretty small, 2, 3, 4, etc. You plot all of your temperatures, 1/temperatures, your natural logs, which I think are negative. Anybody remember?
Yes.
Usually come out as negative small numbers. I don't know. Here's some random stuff. Okay. What we can then do is tell Excel charts. Excel's not giving me all of my features. There we go. We want a scatter plot. And what we can do is with a straight line scatter. What were the x values? 1/temperature. What are our y values? Natural log of k. Excel will now plot a line for us to get this. What's that?
You can figure this stuff out.
And then you can add trend line, line, options, all that fun stuff. Display equation. A lot of work, right? When are you going to be expected to do this? In lab. In lab and in the homework. I want you to see that you can do it. It is something that's necessary to do when you try and solve experiments, but it's not something I'm going to make you do on an exam. What part of this could I make you do on the exam? Here's the graph. What's the equation of a straight line? What is the activation? Okay, careful with the question I asked. If I gave you this graph, okay, we now have the equation of the straight line plotted on there. What did we say the slope of that line was equal to? So we go back to our equation of the straight line format, which is shown on the equation sheet. And our slope was what? Not just activation energy over R, very close. Negative activation energy over R. What would we do? We would say this equals to, oh, clearly I picked the wrong numbers because we end up with a negative activation energy. 10 to the 7th. We'd now solve. Okay, where did we get the 8 times 10 to the negative 7? out of the format of the equation of the straight line? Yes, no? Yes. Hi. Other questions? Well, first, does that cover all your questions? See a whole variety of things there? Probably more than you ever wanted to know. Okay. Other questions with the homework? Textbook problems. I'm seeing a lot of questions about the textbook problems. I tried to change how I worded things on Canvas to hopefully make that a little bit more clear. The textbook problems are not your homework. Connect is your homework. Okay? The textbook problems are there just as supplemental material. If you want more problems to work on, that's where what types of problems I would recommend you do. Okay? Your textbook gives you something like 140 questions per chapter. Okay? And we did that down to 10 to 12. Okay? So you've got some extra problems. For chapter 13, I'm used to having the odds, having answers in the back of the textbook. Apparently your textbook doesn't do that. They do the evens. Okay? So for every chapter after chapter 13, I'll try and pick the problems that you have answers to. Okay? Other questions? Yes. Yes. Yes.
So is that all we really need to know? Because you said something about substitutions.
Said something about substitution.
Like the concentration of the 1/2 equals 1/2 concentration.
Oh, I know what you're talking about. Let me open back up to this so we can get started. So when looking at, you're going to open. So when looking at Halflife, typically you'll see, particularly when we move into chapter 19, they go through and solve the Halflife equation. And they'll end up telling you, I don't have the equation memorized 100%, but I think I'm pretty close. They'll say that the half-life is equal to 0.693 over k. Okay? So that's great. You now have an equation to tell you what the half-life is. However, this equation is only valid at very particular circumstances. When is that one of those particular circumstances? What was that? I think I heard you. You would need to know the rate constant, true. There's something else that's really, really important.
First order?
It must be a first order reaction. Okay? So where this expression is ultimately coming from is the definition of a half-life. Okay? So if we say the half-life, okay, we'll use a symbol here. We'll say T sub 1/2. This is our half-life. Okay? So at the half-life, that means that the concentration at the half-life equals one-half of what we started with. That's the definition of a half-life. So where the heck did that first equation come from, the T half over K? Well, what expression relates time to the rate constant? Or anything to do with rates. It's our time-dependent rate laws. Our time-dependent rate laws are based on particular orders for each of those individual reactions. Oh, this will be good. I'll make myself look like an idiot. Equations. First order reaction is natural log of A at time t equals kt. Thank you. Was it plus? Natural log of A sub 0. This is yet again another reason why I don't make you memorize them, because I don't have them memorized. Okay. What can we do with this? Well, we've got two equations. We can now do our substitutions. If we want to know the time at the half-life, what we'd be saying is we need to solve for k t a half. So let's put that in as a solve. What do we know at t a half? Close, very, very close. A at that time is 1/2 of what it initially was. And we get the natural log, of 1/2 our initial concentration with this equation, we can now try and rearrange it and substitute for T sub half. When we go through all of that mathematical, for lack of a nicer word, masturbation, what do we find out? T a half equals 0.693 over K. Okay? So ultimately, what the textbook is telling you, and this is one of the reasons why I hate how a lot of this material is taught, memorize this equation and you know all the answers. Okay? So you don't have to understand anything about what you're doing. I don't like that, which is why I don't test like that. Which means what I'm going to test for is, do you understand what the half-life is? What is the half-life? It's taking the English and converting it into a mathematical expression and then plugging it into your reactions. Okay? What if it's a second order reaction? Would we still get T a half equals 0.693 over K? No, because we're no longer substituting into our first order expression. Okay? This only works, or this expression only works for a first order reaction. What happens if it's second order? Does somebody have it memorized? It's positive KT now. If I want to solve for T 1/2 now, what do I have to do? Same thing as I did before. But now I have to plug in all those terms, or the new simplifications. We get 1 over, okay? This we can now rearrange as the textbook does. I don't remember what it ends up at, but it rearranges to some new equation. Okay, does that make sense? So the primary thing I'm focusing on is, do you understand what your English is actually saying? And that's one of the hardest parts of this class. What does the English say? What does that convert to mathematically that you can then go through and solve stuff? Okay? So ways I can get around that. I don't ask the half-life. I ask the third life. What's the third life? Okay, it will be the time, we erase that, at which we have 1/3 of what we started with. New equation, substitute in all your values. Okay, kind of makes sense? Does that answer your question? Okay. All we're pretty much going to have time for here is pretty much the definition for equilibrium, which I'm fine with. Okay? So when we move into chapter 14, what we're now going to do is evaluate what equilibrium means and what we can do with it. Okay? So I picked, like I said, I'll change this on future slides. It's not homework, it's text problems. You'll notice, I think I got all of these being even, or all of those are even. So you do have the answers to those in the back of your textbook. So hopefully that'll allow you to check your work. Okay? So we have already seen, so there's a nice little cartoon to kind of explain what's happening. Okay? As you progress forwards to one reaction, you say you clear one path, somebody else is going through and filling in your path. Okay? So what ends up happening is eventually you only get a small space that's actually balanced, that has no snow. Chemistry is going to do a very similar thing. The reactions are going to progress forwards to make products. Those products turn into new reactants and progress backwards to make your new products, which was effectively your reactants. So what you end up with is a very dynamic, static situation. It's kind of counterintuitive. Okay, there's lots of things happening, but the overall result is that nothing changes. Okay? The nice thing about nothing changing, you can now solve for things. Okay? You can get information out of it. Okay? So when we looked at it in kinetics, okay, we saw it really show up when we looked at mechanisms. Okay? So we had to assume that our initial step reached equilibrium. equilibrium was the definition where our reactant or our forward reaction equals our reverse. And we went through and solved for an expression. From this expression, what we wanted to know was the concentration of an intermediate. Okay? So while this expression was helpful, it's not really getting into equilibrium. Okay? We're only trying to use that mathematical expression to get some other piece of information. Okay? So what happens when we move into chapter 14? Well, chapter 14 is the same kind of idea. Okay, the rate forward equals the rate reverse, except now some smart person went through and said instead of solving for the intermediate, or if we remove all information about mechanisms, and this is all we're looking at mathematically, what could we potentially do? Well, they said K1 was what? What is K1? What is K? Rate constant. What is K negative 1? Rate constant for the reverse reaction. What do these brackets imply? Concentrations. So I have two constants but on opposite sides of the equation, and I have concentrations on opposite sides of the equation. So mathematically it makes sense. Let's organize. Let's set all of the concentrations on one side and all of the constants on another side. Okay? So what we end up getting is this new expression. Okay? When does this, I guess not quite yet, when does this officially occur? 5 seconds in, 20 seconds, 4 days? A shrug is a good thing to do. Do you see anything in there about time? No. Okay? We don't have a time relationship when it comes to equilibrium. Time effectively cancels out. K1 and K minus 1, our time units kind of disappear. So we lose all interpretation of time, and all we know is this holds true whatever time happens to be when we reach that point. Okay? So the time is a secondary feature of this. Okay? Well, what's a constant divided by a constant? I like kind of where you're going with 1, but we need to get a little bit less specific with that. It's a constant. 1 happens to be a constant, but it doesn't have to be 1. It can be any constant. Okay? So let's come up with a new expression or a new numeric or a new symbol to imply that constant. Lucky for us, they decided to be really consistent and pick K. Okay? Except now it's not lowercase k, it's capital K, so of course it's so different. Okay? Realize that, particularly when it comes to exam 1. Okay, we've got a bit of an issue. Rate constants, okay, where we're looking at rates, we've got a time value associated with those, some kind of importance when it comes to time. When we move to equilibrium, we're looking at a K again, except no time dependence, which means the things that control rate constants don't necessarily control equilibrium constants. So you have to be very careful with what you're using in each of these cases. Okay? We can simplify this out, and one of the expressions or one of the things that we determine when we look at equilibrium constants, it's your product concentrations divided by your reactant concentrations. Okay? So while the equilibrium constant is determined from your rate constant, they're controlled by differing things. Okay? So we'll now, what do I got? I'm going to say I don't have any more time. Okay? So we'll go ahead and stop there and pick up on Tuesday.